Today we're actually going to be starting Chapter 9 and moving away from Chapter 8. There's only a couple sections left in Chapter 8 anyway, but I think Chapter 9 is a pretty important one to get through, especially considering where we are right now, having a pandemic and having to stay at home. This one goes directly with basically that same type of concept of spreading some kind of virus or disease. So the first section we're going to talk about today is 9.1, exponential growth. Example 1. Mike is sick with the flu, but he still comes to school on Monday. He arrives at 8 a.m., and by 9 a.m., the first hour, Mike has already infected one of his friends, Jose. By 10 a.m., hour 2, Jose has infected one of his friends, Bill, and Mike also infects another one of his friends, Lisa. This continues to happen all day long. If each person with the flu infects another person each hour, how many students are infected by 3 p.m., hour 7? We're going to complete the table and then graph the points in the grid below. But before we get there, let's kind of make a little picture or web what's going on. So we have Mike. Here's Mike. He's sick. He wakes up sick. He has the flu or whatever. He decides to go to school anyway. So then by the time 1 hour elapses at school from 8 to 9 p.m., he goes to his buddy. He talks to one of his friends, Jose, gets him sick. And then after that, another hour, Mike goes and talks to somebody else, another friend. Mike talks to Lisa, gets her sick, and Jose then goes and talks to Bill. So this is over the course of 2 hours. Now we have 4 people sick. So I have this table down here below that we're going to fill out over the course of time. If this continues to happen, the next hour, Mike talks to somebody else. Lisa talks to somebody else. Jose talks to somebody. And then Bill also talks to somebody. It just keeps kind of expanding every single hour. Each additional person that gets sick also talks to an additional person. So we look at the table down here. It's the number of students infected with the flu by the hour. We call hour 0 when Mike was sick in the morning before he even got to school. So hour 0 is by the time he gets to school at 8 a.m. This would be 8 a.m. He's the only person sick in the school. Then he talks to Jose, which makes it 2 people sick total. This is 9 a.m. And we keep going from there. Hour 1 was 2 people. And then hour 2, what happens? Mike talks to Lisa. So we get this thing going up here. And then Jose talks to Bill. So hour 2, we have 4 people. Bill, Jose, Mike, Lisa. How many people would there be in hour 3? Well, I just drew it up here. Mike talks to somebody. Lisa talks to somebody. Jose's talking to somebody, and so is Bill. How many is that total? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 people total sick. So you could keep drawing this and expanding the web up above, or maybe you could just kind of see the pattern of what's going on. How do we get from 1 to 2, 2 to 4, 4 to 8, and then what would happen after that, instead of constantly drawing the picture. So if we look at that, can you see the pattern of what hour 4 would be if all these people up here, including Mike, Lisa, Jose, and Bill, and all the new students, if they talk to one other person in that next hour, how many people would be in hour 4? If you look at it, maybe say, oh, well, it looks like it's just kind of doubling itself. 1 to 2, 2 to 4, 48. So how would we get to the next number? Just double it, and you'd be correct. That would give you 16. And then we do it again next hour. All those people talk to somebody else. 16 goes to 32. There you go, double it again, hour 6. Now we're at 64. And the last hour, if we double it again, we're at 128. So at what point in time are we at here? We went from 8 to 9. This is 10, 11, 12, 1, 2, and you squeeze it in at the end here. This is 3 p.m., basically the end of the day of school. So within one day, we have a total of 128 people that are sick. Now, this is only if each person interacted with one other person each hour, which most likely in school you're going to interact with more than one person, so it actually grows a lot faster than this. So 128 is actually pretty conservative considering how many people you interact with when you're at school. Usually not just one person or one friend per hour. Part B, if the school has 1,000 students enrolled, which our school has a little bit more than that. I think we're at like 1,200 or so. What percentage of the student body has the flu by 3 p.m.? So we just talked about this. Hour 7 is your 3 p.m. when school's over. So there's 128 that are infected. How would we figure out a percentage of that? Well, you just take the total number of people that are infected, 128, and we divide that by the total number of students. 128 divided by 1,000. You just divide that out in your calculator. So what would that be? You can use your phone, or if you have a calculator on the computer, that's 0.128. That's a decimal. If you multiply it by 100, or move the decimal place over twice, so you have about 12.8%, or maybe even close to 13% are infected with the flu. Then we will go over here and we'll graph and see what kind of graph this looks like before we go to part C. So hour 0, the only person that's sick in the morning was Mike. So that's 1. So 0 hour. This is hours in the school day, and then students with the flu. So 0 hours. There's only 1. So this goes by 10. So you're gonna have to just make your best guess on how to graph it. So here's 1 is my guess. Hour 1, it is 2. Very slow growth here. Not super accurate here. Hour 2 is 4. Still not going anywhere. Remember, the first one here is 10. So we haven't reached 10 yet. Hour 3 is 8. Almost close to 10. Now we're starting to shoot up a little bit here. So 4 is 16. So that's going to be maybe like here-ish. Between the 10 and the 20. 5 is 32. 32 is probably about here. 6 is 64. 64 is probably here. And then the last hour we have at 3 p.m. is 128. 128. There we go. And then we're going to try my best to connect these dots to see what the graph looks like here. So it looks pretty level. It's only increasing very slowly at first. And then by the time you hit day 3 to 4, or hour 3 or 4, it really jumps. Oh boy. There we go. And it's going to continue going in this path. So try your best to connect those dots. I can't do so well. So this is just within one day, 8 a.m. to 3 p.m. And you can see the progression is kind of slow, but then it really shoots up into the air pretty quick within a few short hours, and still within the first day. So what kind of equation would this look like? Right? If I'm looking at something, y equals what? What can we put in there to describe this kind of graph? Now, one thing that a lot of students guess is something like kind of like a parabola almost, although it's pretty flat at the bottom. But it does kind of look like a parabola. So a lot of students think it's x squared. It's not quite x squared. It's actually something that grows a lot faster than that. Some people may think it's just a higher power, like x cubed. It's actually something completely different than this, although this does grow faster than x squared. But we need something that actually grows a little bit faster than that even. This is what we talk about as something called an exponential function. Exactly what's going on with this whole pandemic is that you might have heard them say like how this kind of virus grows exponentially. That means that's the kind of trajectory that the graph is showing right here that we have with Mike and the flu at school. You have this exponential graph where things are ramping up really quickly over a short period of time and affecting a lot of people. So what does it actually look like? So down here, exponential function, the function defined by the equation y equals a times b to the x power. So it looks a little different from probably what you're used to. The x variable that you're so used to seeing, like an x squared or x cubed, is actually in the exponent, which is why they call it exponential functions, because the variable is in the exponent. Then you have some restrictions over here. A cannot be equal to 0. Obviously, if 0 is in there, that would make the whole thing 0. B has to be greater than 1, and you'll probably see that a little later, why b has to be greater than 1 to make it an exponential function. And then b can also not be equal to 1, because if b was 1, then 1 raised to any power would make the whole thing 1. So this actually doesn't even make an exponential function if b is 1. So you have a couple of restrictions there, but if you meet those guidelines, then that's an exponential function. So to look at a and b here, we have something called the growth factor. So what makes it grow a certain rate is the actual letter b. B is the growth factor, whatever number we put there. A and b are going to be numbers. A starting point, or your y-intercept, so kind of where it starts with a number of people who are sick or whatever you're talking about, is your y-intercept, and that's the number out in front, a. So it's a times b, your growth factor, to the x power. So let's try graphing one. Example 2, graph an exponential function. Graph the following equations by using the table. So we're going to plug in these numbers on the left column here, plug them in for x, and see what we get. So I'll do a couple of them off to the side, then we can try to graph them. So we plug in -2, we have 2 to the -2. How do we handle that? We can make it over 1 and flip it and make the exponent positive. I hope you remember how to do that. So this becomes a positive exponent. Now it's 1 over 2 squared, or 1/4. So 1/4, if I can squeeze that in there. So it's pretty tiny. -2 is 1/4. If I plug in -1, so it's 2 to the -1. Actually, let me put it on the other side. 2 to the -1, which means you can throw it on the bottom and make it positive. So it's 2 to the first on the bottom, or just 1/2. Plug in 0. What happens when you plug in 0? What's 2 to the 0? You should know that as well. What is 2 to the 0? That is always 1. A number to the 0 power is 1. Plug in 1. That's 2 to the first power, which is 2. And then 2 squared, which is 4. Maybe I can space this out. I'm not sure if I'll be able to or not. I might be able to go every other one. So it's 1. This could be 1, 2, and then -1, -2. And I'm actually going to get rid of the lines because these dots are going to be really close to the actual axis. So -2 is is 1/4. And maybe I can even spread this out to be 4. So 1, 2, 3, 4. Can I go over 2? 1, 2, 3. I'm going to try that. This will be 1. This will be 2. This will be 3. And I'll put an extra box to make it 4. Because I only need to go up to 4. Really space this out a little bit. So -2 is 1/4. So that means that this would be 1/2. So it has to be right here. 1/2 of that. -1 is 1/2. So that would be right here. At 0, it's 1. So that's right here. 1 is 2. And at 2, it's 4. So it spreads it out nicely. It's a lot easier to graph. And then we have this shape here. It actually goes both directions, left and right. And you can see the kind of the similar graph that we had before. It's growing fast. May not look like as fast as the first one here with the flu, but it's the same kind of graph, an exponential curve here. All right, example 3. Determine whether the following are exponential functions. This is actually really simple. Don't get confused with what's going on here. It's not that difficult. If you go back to the definition, really all we're looking for, the definition up here, is defined by the equation y equals a times b to the x. So how do you know where it's exponential function? All we need to have is the x variable in the exponent position. That's pretty much it. So let's go back down. F of x equals 3 times 7 to the x. Is it exponential? Yes or no? Yes, it is. Why? X is in the exponent. That's it. Let's go down to part C. We'll go over to the other column in a second. F of x equals 3.7 to the x. Now, there may not be a number out in front being multiplied like in part A, but that's okay. Sometimes that number you don't see. Particularly, that would be the number 1. It'd be 1 times that. Can this be a decimal? 3.7? Sure. The growth factor can be 3.7. So that is also an exponential. Just looking at this. Is it in the exponent? Part B, x to the 3.7. So if they flip that around from part C, is that an exponential function? Well, the exponent is a number. It's not just x, so no. And the last one, which is almost the exact same thing as part A, they just put a parenthesis around the 7 instead, which is fine. You're allowed to do that. That would be a yes as well. X is in the exponent. Only have 2 more examples left. If I'm going too fast, whatever, you can just pause it and rewind, which is the beauty of having a video. Graph the following equation, identify the following. So now we actually have a number out front, that 3 being multiplied by 2, and then raise the exponent. Be careful when you do these, because you have to do PEMDAS, and you have to do the exponent portion first before you multiply by the number out front. So let's do some of these together here. We have -2 that's going to be put in for the exponent. So we have -2. It'd be 3 times 2 to the -2. So how do you solve that? Should have gave myself more room. This is 3 times 1 over 2 squared. 3 times 1 over 4. See why I put over 2 there? This is a negative exponent. 3 times 1 over 4, just make it 3 over 1, go across top and bottom. This is 3/4. So you can continue doing this in the same manner. I'm just going to erase it and just probably do it again. Change this to a -1, which looks very similar when you solve this. If you put a -1 in there, it makes it 1 over 2. Put it over 1, 3 over 1 times 1/2. And that would be 3 over 2, which is, what, 1.5, 1.5. Plug in 0, so 3 times 2 to the 0. Any number to the 0 power is 1, so it's 3 times 1, or 3. Plug in 1. Hopefully I have enough room to do all this. 3 times 2 to the first, so it's just 3 times 2, or 6. And then the last one, three times 2 squared, which would be 3 times 4. Got to do the exponent first. You get 12. May not be able to graph 12 on this graph. That's okay. We'll get close. So let's go ahead and graph before we answer these parts. -2. Can I space it out again? Yeah, I'll space it out again. So this is 1, 2, and then -1, 1, 2, -2. Change the color again. So -2 is 3/4. What do I want to go by? I guess I'll just go by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is going to be pretty far out there, but we can at least get the other ones on there. -2 is 3/4. So that would probably be like right here. -1 is 1.5, so about here. 0 is 3. 1, 2, this is 3 up here. Put a big dot there. 1 is 6. 4, 5, 6 right here. And then 2 is where it gets really crazy off the charts. It's 12, so that's going to be like up here. All right, so let's draw it as best we can. So I have the same curve as before. Okay. So let's talk about the graph a little bit. What is the y-intercept? You should be able to see that from the graph and actually from the table. So when you plug in 0, you get what? At 0, it crosses right here at 3. So it's 3. Y equals 3. What's the x-intercept? Where is it across the x-axis? Well, we haven't really gone too far to the left to see where it crosses the x-axis. And maybe you can see it, maybe you can't, but it actually does not. This is not possible. Or no, actually I should say it's none. What's the x-intercept? There's none. We talked a long time ago about something called an asymptote. That was when the graph gets closer and closer to a line but never touches it. That is exactly what the x-axis is doing here. It is considered an asymptote. The graph will get closer to it, but it will never touch. Maybe I'll talk about that in some other video. The domain, you can go left and right forever. The graph continues going this direction. It continues getting wider and going out to the right. So the domain is all real numbers. The range, we just said it does not come down and touch the x-axis. So it cannot go down, dip below in the negatives at all in the y values. So it has to be everything bigger than 0. So range is y is greater than 0. We cannot say it's equal to 0 because it doesn't touch 0. It will actually not come down and touch 0 and touch the x-axis. Hopefully that's okay. Okay. Exponential growth.